So now let's take a look at example problem 1.5.5 from our text. This problem here, we're going to be sizing a motor for a lead screw. Now I've taken what we have given in the word problem for this example in the text and kind of underlined and highlighted a few key things that we're going to be able to take away from the problem statement. So they give us quite a bit of information within this here. So in the problem, they tell us to neglect friction. So there's an assumption that we can make. We have zero friction. And they ask us to estimate the torque. So there's what we're looking for right there, required to accelerate a 100 kilogram load. So we have our load right here and our units. And they want us to go from rest, so we know it's starting at 0, to a speed of 0.2 meters per second in a time given to us as 0.1 seconds. Using a steel lead screw of length, they give us the length of that lead screw of 1.1 meters, and a radius they tell us is 0.013 meters. So again, they've given us the units there. They tell us that the screw lead, L, is equal to 0.005 meters per revolution. And they also tell us that the motor inertia is 2 times 10 to the negative fourth kilograms per meter cubed. So we'll pay attention to these units here. And they tell us also that the density of the steel, so it tells us it was steel, is going to be 7,700 kilograms per meter cubed. And I have here a diagram for a general lead screw with the variables shown here. So if we look through, one of the first things we can do is really try to understand just from the problem statement what they're asking us to solve for. And I put this in italics here. We want torque. So a couple things we can do when we're going through a solution. One thing is, okay, I know I'm looking for torque. What are my governing equations involving torque? And kind of work backwards and plug in our variables along the way of what I do know is given the problem statement in order to calculate our torque. Another thing that we need to do is pay attention to all of our units, make sure everything's given in the correct units, and that we do our conversions as necessary. So from here, the next step that we want to do is take all of this vast amount of information that's given in the problem statement, break it down clearly into what I know, what they're giving me in this here, write each thing out individually with the correct units and what it corresponds to, and then also write out a separate section of what they're asking us to solve for. So that'll be the next step in our solution, is to handwrite all of this out. Now that we've had a chance to look through the problem statement, for example 1.5.1, the next step is to figure out what's actually given information, write it down clearly in one location here so we can reference back to it. So you can see I have the variable name, what it is as it relates to the problem, the value, and the unit. So all four of those are very important to have, especially as we start plugging and chugging for a long involved problem. We need to keep referencing back to these and making sure that we're in the right units and doing unit analysis as necessary. So as I read through the problem statement, I see that they gave me the mass. Variable M, this has a value of 100 in units of kilograms. I also see the screw load. I have right here the variable L. It's 0.005 meters per revolution. We have the radius, R, is equal to 0.013 in meters. We have the density given to us by rho is equal to 7,700 kilograms per meter cubed. Time is T equal to 0.1 in seconds. We have our length. I'm just leaving this as length, and that's one thing to note. Typically, we've seen L before as length. Sometimes you can write this as a lowercase l, but just to avoid confusion, I'm leaving it written out as length. So length is equal to 1.1 meters. I have my motor inertia, I sub m, is equal to 2 times 10 to the negative fourth in units of kilograms times meters squared. I have my velocity here, v, is equal to 0.2 meters per second. So that's everything I have that's given to me in the problem statement, or given diagram if there was one. The next thing I want to do is figure out what are they asking me to solve for. So what they're asking us to solve for in this problem here is the required torque. So our T value here for torque. I've drawn out our generic diagram here for our lead screw with the variables associated with it. And the next thing we want to do is make any assumptions that we need to in order to solve this problem. Well, one assumption they give us right in the problem statement is that we're going to assume that there's no friction. So now I have everything I need in one spot here on my first page. I have all of my givens, what I'm looking to solve for, and any assumptions I'm making. So this is great to have this all on one page. I haven't started my solution. That way I can always flip back to this first page. Okay, what was my value for L? What was my value for time? Okay, what were my units that it was given in? Oftentimes, I'll do conversions right here for unit analysis. If I wanted time in terms of minutes or hours, I'd do this out. Or if I needed my length in terms of inches or feet, I would do that out there. Just so I have it all in one spot to reference back and have less involvement in the solution of the problems to keep the complexity a little bit less, keep things a little more simplified. So again, here's our first page. We can reference back to this as needed. So the next step is to start our solution. So in order to start a solution, we really want to take a look through all those given values from the problem statement, understand what they're asking us to solve for, and from there, pick a governing equation that we can use to start the solution for this problem. For in this case here, we have a lot of given data, and in order to identify this governing equation, we're going to go back to page 27 of our textbook and take a look at equation 1.5.7. So here we have I sub L, which is the equivalent load inertia, and L is our screw lead. So that's information that I have given me in the problem statement. I take a look at this relationship here. Our I sub L is equal to ML squared over 4 pi squared, where I know I have my mass given to me in the problem. I know I have my L value given to me in the problem. These are constants that I can plug right in for. So therefore, I can plug directly into this and solve for my equivalent load inertia. So that's the next step in this problem here, is take this governing equation. I like to leave it written out in terms of variables. Say exactly where it is. And this is going to be important for you as well, because this is how the TA and the grader are going to be able to give you partial credit. If you just plug things in, box in an answer, and they don't know where your work came from, they're not going to be able to award you partial credit. So if you look at the rubric I've given for how I'm going to grade homework problems and exam problems, you'll see that a good portion it comes from identifying your governing equations. So I have this here. Now the next start is to plug in my known values. So again, I go back to this general equation, plug in my known values. So I know I have my L value here. Again, for my screw lead, which is given to me as 0.005 in units of meters per revolution. This value is squared there. I have my mass value given to me as 100 kilograms. I can plug in for that there. So kilograms, meters, revolutions squared over pi. 4 pi squared down here. I can take a look and see what units cancel out. And I know what units I want this in for inertia is kilograms per meter squared. I double check, do my unit analysis. Yes, that works out. Plug and chug. You can put this in your calculator, do it by hand. MATLAB, Excel, whatever works best for you. Pretty straightforward plug and chug problem there. I have my I sub L, or my equivalent load inertia, now equal to 6.3326 times 10 to the negative fifth. Again, in units of kilograms times meters squared. I box this. And this is going to be helpful so I can quickly reference back to this when I need it later on. This isn't my final solution. What I'm looking for, again, is torque here. So this is one step along the way. But I'm still going to box it so I can quickly reference back to it. So in the next step of my solution, we need to calculate the mass of the screw. So we need to do a little recall for some previous courses, previous textbooks. We know that mass is equal to our density times our volume, or rho times V when we're talking about our variables. Where volume here is going to be area times the length. And area is going to be dependent on the shape. So I'm slowly plugging in from a basic equation here. Now in terms of volume, I can add this in. So I plug this back in, the area times length, back into my mass equation. So mass, when I plug that back in, is equal to rho A times my length here. And again, I'm using the word length for length just so we don't get confused in this problem here. So what do I know? So I take everything from page 1 that I know for values, and I can plug them back in here. But I want to make a little note to myself. Okay, I know my density, my rho is given to me, 7,700. I still write down my units of kilograms per meter cubed. My area, I know my area is pi r squared. So again, I can plug in my value for my r now from the beginning part of the problem. R is equal to 0.013 meters. That value squared there. My length is 1.1 meters, so I can plug that in there. So I have my rho, I have my area based off pi r squared, and I have my length here. Pay attention to my units. I can plug these all back in now to my governing equation up here for my mass of the screw. So I plug this back in here, take these values I've known. So my mass times my density of 7,700, plug that in there. Write down my units below it here in red, just so we can do some unit analysis and double check. Pi r squared, there's my r with units of m squared, meters squared, 0.013 squared. And then I have my length over here of 1.1 in meters. So meters times meters squared here times meters cubed in the bottom. These are going to cancel there, which just leaves us with units of kilograms, which it's a mass. So that is what we should have. So that's a great double check for us to make sure our equation is right, because we've kind of plugged equations in equations. Unit analysis really helps us to confirm that. So our mass, we plug this all in, is 4.797 kilograms. So for the next step in our solution, we want to calculate the inertia of the screw. Now this governing equation comes from page 27 in our textbook, and we're going to equation 1.5.8 for this here. Equation 1.5.8 gives us I sub s is equal to 1/2 m sub s times r squared. Now we can see our r is a capital R here, and our m is an m sub s. So this is the mass of the screw. This is what we previously calculated on the page before this in our solution. Now, if we hadn't known to calculate that in advance, we could get to this problem and go back and solve for it. No worries there. The relationship here is realize that our capital R from this equation 1.5.8 is really what we're calling our lowercase r given to us in the problem statement. We know that's a given value of 0.013 meters. So everything that I know for this equation here, I write out here, my m sub s is equal to my mass is equal to 4.497 in kilograms. Capital R is equal to R of 0.013 meters. This is what I calculated on the previous page there for my m sub s. Now I can take these values that I have and plug back into equation 1.5.8 here, and that's what I do down here. So my I sub s is equal to 1/2 my m sub s value from the previous page of 4.497 in kilograms. My radius given to me is 0.013 meters. This value is going to be squared from this equation there, so therefore my units are mass squared in kilograms. So now that's exactly what I expect for inertia. So I sub s is equal to, when I do all my math, 3.8 times 10 to the negative 4th in units of kilograms times meters squared. So the next thing I want to look at is calculating the inertia of the entire system. So far we've been calculating the inertia of individual components within the system here, but we want to look at the system as a whole. So our total inertia for the system is given by this relationship here. So I is equal to our I sub m, which is our motor inertia, given to us in the problem statement, our I sub L, which we've calculated, our equivalent load inertia, and our I sub S that we've also calculated for our screw inertia. Now, for each of these individual components, I've already calculated these, my I sub m, my I sub L, my I sub S. My I sub m I found to be 2 times 10 to the negative 4th units of kilograms times meters squared. Units check. I sub L, 6.3326 times 10 to the negative 5th units of kilograms times meters squared again. Check. And our I sub S for the screw inertia, 3.8 times 10 to the negative 4th kilograms times meters squared. So now I can take all three of these values, plug them back up into my equation for the total system inertia there. I do that. I is equal to 2 times 10 to the negative 4th times 6.3326 times 10 to the negative 5th times 3.8 times 10 to the negative 4th, all in units of kilograms times meters squared. I do out my math here. My inertia for the entire system now is 6.4333 times 10 to the negative 4th in units of kilograms per meter squared. Box this in. It still isn't my final answer. Again, I remind myself, I'll go back to the first page, I'm looking for torque. This is one more step along the way to getting there. So now we've gotten to the point in our solution, finally, where we're actually going to begin calculating the torque. Now, this may have been a place you actually wanted to start when you're looking at the problem statement and what they're asking us to solve for, and they wanted us to solve for the required torque. So we can see this is our general equation of motion for the required torque here, and this is derived from equation 1.5.2 on page 25 of our textbook. You see the torque is equal to our I, inertia of the whole system, times our omega dot. So this right here is why we spent the whole first part of the solution to this problem solving for the individual inertias of each component of the system to calculate the total inertial I for the system as a whole in order to plug back into this relationship for our equation of motion for the required torque here. So with this here, T is my torque, I is my inertia, my omega dot is my angular acceleration. So the next step in this here, I already know I've calculated my I know T is what I'm looking for, my torque here. Let's work on this right here, my omega dot or my angular acceleration. So we can take a look at it if we scroll down here a little further, is that the linear displacement x of the mass related by the rotation of the angle theta of the screw by this relationship here. And this comes from page 27 of our text. So what I have here is x, or our load translation, is equal to L times our theta here over 2 pi. So now we can do a little bit of calculus here, take some derivatives of this in order to get from position and our displacement here, velocity, acceleration. So our velocity, we take the first time derivative of our position here. So take the derivative of this here. This goes from L theta 2 pi to L omega, where omega is theta dot over 2 pi. So then if we want the acceleration or the derivative of our velocity here, our x double dot, second derivative of our position here with respect to time, we end up with the right side of the equation. L, take the derivative of this is our omega dot, which is exactly what we're looking for up here, our angular acceleration, or omega dot there. We've all seen it in terms of alpha before. So now we have a relationship here that our acceleration is equal to L omega dot over 2 pi. So now with that relationship that we've just come up with here for our acceleration, our x double dot equal to L omega dot, or angular acceleration, over 2 pi, we can now rearrange this and solve this for our omega dot here, because that's what we're going to need to have for a value to plug back into our torque equation from the previous page. So we rearrange this, we multiply this 2 pi over here, divide by L, we end up with omega dot equal to 2 pi x double dot, or acceleration, divided by L here. So what do we know? Well, x double dot is the change in velocity relative to time. So x double dot is equal to first time derivative of our x dot here, or our change in our x dot, or velocity, with respect to time. So what do we know in our problem? So we go back to our page 1 again. This is why it's great to have that all by itself there. Okay, what was my velocity? What was it here? Well, my velocity was given to me as 0.2 meters per second squared. We know it starts from rest. So our change of velocity from rest to that is going to be 0.2 minus 0 in units per meter per second. We know at initial time it starts at 0, and we know time of interest here, when we have that velocity, is at 0.1 seconds. So we know our change in time, or our delta t, is 0.1 minus 0 seconds. So I can plug that in here. So again, if we go back up to here where this is change in velocity over change in time, we know our change in velocity, we know our change in time. We can plug back in to solve for our acceleration here. So change in velocity over change in time is 0.21 meters per second divided by 0.1 seconds. Again, our unit analysis lets us know that's in meters per second squared, which is what we expect acceleration to be in. So our acceleration, or our x double dot here, is equal to 2 meters per second squared. We do out our math. So now we can go back to our relationship with omega dot and our torque. So we go back to our omega dot relationship here. So omega dot is equal to 2 pi x double dot divided by L, where this is our acceleration that we've just solved for on the previous page. So we know here, okay, my x double dot is 2 meters per second squared that we just solved for. My L is given to me in the problem statement of 0.005 meters per revolution. So I can plug that information back into this relationship here for my omega dot, or my angular acceleration. So angular acceleration is equal to 2 pi times my x double dot, or my acceleration of 2 meters per second squared, divided by L over here of 0.005 units of meters per revolution. I plug this in, I get my angular acceleration, or my omega dot, is equal to 2,513 in units of radians per second when we do our unit analysis here. So that can then be plugged back into our equation for torque, which is finally, we're reaching the point where we're getting to what they asked us to solve for our torque. The problem statement here, so torque, recall, is equal to that total system inertia times this angular acceleration. Now we have a value for angular acceleration. We have a value for our inertia that we solved for at the beginning part of the solution here. Plug that in. Torque is equal to 6.4333 times 10 to the negative fourth in units of kilograms per meter squared for our total system inertia. And our angular acceleration from this here is 2,513 radians per second squared. I do out my math, I do out my unit analysis, I end up with torque is equal to 1.6168 in units of newtons times meters, which is correction units for torque. Great double check. That's our final solution to the problem there.